Hi, this is the final result of this video. This is a series where we build a 3D RPG in TypeScript. All of the code is in the description below, and you can look at the playlist for other videos on different topics. In this video, we're going to create a basic terrain and billboards for our trees and other kinds of objects in our game. Let's get started. Starting off, I have VS Code open to a completely empty folder. And right at the start, I think this is a great place where we can separate our code into engine and game code. That way, if you want to use the engine later for other games, you can do that. Let's create two folders. So I'll create our engine folder, and then we'll create the game folder. For each one of these, we'll use a package.json file, which says that it is a module. So let's come in here, we'll create a package.json file. And we'll add some metadata to this. Now, this is the name of this particular module, this engine. We set it private to true, and then the version you can set to whichever you want. This means that we're using modern JavaScript with modules that let you export. And then this will be the entry point of that. We'll use GL matrix as a dependency. This will allow us to do math later. And then we'll also add TypeScript. Let's come over here and we'll do the game folder and we'll do the same thing. Let's create a package.json for here. So this will be somewhat similar, except for instead of an entry point, we're going to use Vite instead. Vite is a really nice library that lets you render a web page and have a bunch of TypeScripts or JavaScripts. Be able to hot reload and then also be able to bundle everything together once you want to actually put it on a website. We'll create the following scripts. This will be our dev server, which has hot reloading. And then this is a script that we can use that actually builds everything when you're ready to package it. We'll use our engine over here. So this links all the code in our engine to our game. And then we'll end up using Vite, and then similarly, we'll also use TypeScript. Now this is great, but workspaces are really powerful because we can run our scripts across just on the root and bring everything together. So let's create a third package.json outside of both of these folders. So this package.json ties everything together. We use workspaces, which says we're using these two packages. And what's great is we can actually run these scripts on the root. It's going to make it really nice and convenient for us to just run npm run dev. And it'll end up actually going to the game module and then running this command in the game module. Same thing over here. So we can just run npm run build right on the root, and it just goes to the module it needs to go. This linting is very useful for just checking if you have errors. Now, TypeScript is really powerful because it lets us choose what rules we want to use. And let's get that set up real quick. Let's create a tsconfig.json file at the root. This will be our root sort of tsconfig.json, which tells TypeScript that we have these our code basically in these two places. And we'll end up creating this file here. Let's go ahead and do that now. Let's create a tsconfig base.json. This is where we're going to define the rules that apply to all of our modules across everything. This is a really helpful tsconfig that I think is very helpful. I won't go over too many of these. This is the version. This is the libraries that we're using. We're using DOM stuff because we're using the canvas. This tells it how to output. I do want to highlight this one. This right here says to TypeScript to be strict in checking, which can be helpful for finding issues as you're writing your code. And then all of these are various different rules that are involved with that. Like this, for example, helps with not going outside of arrays. To be honest, with these, I've had to kind of look them up, and this changes over time, and I just kind of paste it into my project, and it checks things for me, and it's awesome. You can look these up if you're more curious. You can really customize this, and it's really awesome. So the benefit of doing this here is that now we don't have to do all of this in each one of our modules. So let's come in here and let's go to game, and let's say tsconfig.json. And what's really cool is we can just use this and just reference that file that we did previously. And then we're going to say we're going to include this in the checking. And then we'll exclude the distribution folder, which is where our output stuff will go when we build. And we'll also exclude this because this is going to be massive. We don't need to be checking other people's code, just really our own. Let's go ahead and go to the engine code and we'll do the same thing. tsconfig, if I can spell right, .json. It's pretty much a copy paste. Again, we're also referencing the tsconfig here in this package. So with all that being set up, let's get to actually seeing a web page. So let's come over here to game, and we're going to do index.html. Now in VS Code, what you can do is you can just use the exclamation mark and hit enter, and then it will generate this. I think this is a plugin. It's like HTML. And yeah, there's different ones. I think it might be built into VS Code. But yeah. And then what we'll do is we'll say 3D TypeScript RPG, or whatever you want to put here. You can put whatever kind of title there. And then let's also put a canvas. And then this is where we're going to draw everything into. Okay, to get this started, let's go ahead and we'll open a terminal. And we're at the root of our project. Now what we can do, if everything is set up correctly, is we can do npm install. And what it's going to do, because we're using workspaces, is it's actually going to search each one of these package.jsons for different packages. Yeah, so it added a bunch. Even though the root doesn't have any dependencies in it, it added the dependencies from here. And that's what's really nice, is when you want to just refresh all of the dependencies in your whole project, you just do it from the root. And then if we also set up everything correctly, we can just do npm run dev right from the root, and it should use the game. And yeah, there we go. Now, for some reason, if you hit an issue here, just check your package.jsons and just make sure that everything's good. Okay, it created a dev server. It's normally 5173. I think I've got another one running. Let's come over here and let's control click, or if you're on a Mac, command click. And now I actually see a web page of this RPG. Now, however you want to do it, if you have a different screen, you can put it over there, or you can just go like this and put, VS Code over here, or whatever you want to do. Let's come over here. We'll adjust this. Okay. And then the cool thing about Vite, before we even get into anything, is that I can just say like, hi, how are you? And then it hot reloads, right? There's a canvas in front of it that we have here. That's why it put it over there. But yeah, so this is what's cool about Vite, is that it just sort of hot reloads as you edit the code and things. And you can just leave the server on. And if for any reason it stops, you can just go back into your terminal. There's going to be a bunch of output here. Control C will stop it, and you do clear. And then you can come in and you can just do npm run dev anytime that you want to run the server again. And it'll give you a bunch of those to do. So from here, what we're going to do is we're going to connect our TypeScript code and make sure that TypeScript works. So in the game, let's come over here and let's do main.ts. And then let's just do something really basic. Let's do console.log, hi, this works. And then what we're going to do is we'll go into our index.html. And I like to put, you can do different things, but I like to put the script down here. We need to do this. We need to do source, and then our main.ts file. And then we need to do one other thing, because we're going to use multiple different files. We're going to use type module. And this tells the code to load multiple different things. When we actually output everything, it's just going to output to one file. If this worked, let's come over here and you can right click. Every browser is different. There might be an inspect, or it might be in your properties. I know for here on Firefox, there's the web developer tools, and that's what you can use there. But let's come over here and let's do inspect. And then if we go to the console, and then we should see that hi, this works. That means that our TypeScript is now working and good to go. Okay, so let's get rid of this and let's go from there. So our next goal is to actually get WebGL set up, which is going to draw all the objects and things on our screen. And we want to get it drawing into this canvas. So let's go ahead and let's go over to our engine, and we'll create a new file called main.ts. Okay, so we're going to make our engine class, and I put static here because the engine is going to be just globally available everywhere. I think that this is an easy pattern for now that we can do. We have this nice function loop, which is going to run every frame. And what it does is it calls request animation frame. What this does is this goes to the browser and says, okay, the next time that you draw a frame, call my function here. So the function itself is just calling again over and over and over, as long as this browser is open. Request animation frame will try to do that, but if your computer doesn't complete a frame within the monitor refresh rate, then it might be slightly slower. So on a normal monitor, it's probably 60 hertz, but you also have monitors that have higher refresh rates if you've got a gaming computer or something like that. So this may call it faster. Let's come over here, and what we're going to do in our engine is we're going to create a new folder called visual, and then we're going to create a new file called visual.ts. This folder is where all of our graphics code is going to live. So the first step in doing this is clearing the entire screen with a single color. So let's also create another file called color.ts. Color.ts. Not rs, let's do ts. There we go. Throughout this series, I'm going to add a lot of comments, but don't feel like you have to write anything that is in gray here. So if there's these slashes, don't feel like you have to write it. But yeah, we're going to create a class for just defining a color. And we'll have a red, green, and blue value. And then we'll also have an alpha, which determines how visible something is. So 0 is completely invisible. 1 is fully solidly visible. And then anything in between that, you can start to see through it, like glass or water. And then we'll initialize our new color. And the alpha, we're going to have a default of 1, just in case we don't want to specify it. Another thing that's really helpful is just predefining different colors. So we have a static read-only color called blue, and we're saying red is 0 and green is 0 and blue is 1, which is 100%. And this lets you in your code do something like this, where you can just say, I just want the color blue. I don't really care. I don't want to like create a new color. You can make as many of these as you need. Now with this being said, let's go into visual.ts. We'll create a class for all of the visuals in our game. We're going to hold a reference to the canvas object that we created earlier in our HTML. This is going to allow us to draw into the page. And now that we've done it, we'll create a clear color. And as you type in VS Code, if you've got the TypeScript one, notice how I can just go to color and I can hit enter, and it automatically adds the import here. If you go into your extensions here and you have the TypeScript extension, it can actually know to do that. I think in the most recent version, Visual Studio doesn't need that, but if you have an older version, you might need to do the plugin. So this clear color is going to basically be what we start off every frame with. Otherwise, you're going to have pixels from the previous frame. When we create a new visual engine for our game, we're going to get a reference to the canvas. This is going to look up the canvas and just say, no, trust me. We've got it somewhere on the page. Let's define a new clear color. So this is going to be a little bit red, but mostly it's going to be blue and green. So it'll be kind of a nice green sky blue color. Now, sometimes in Visual Studio, you might notice there's a error here. Sometimes when you're using the imports, it puts this type thing in here. So if you're, sometimes there's a reason to use that if you're just referencing the type itself like here. But let's go in and let's just get rid of that. And then that'll get that error out of there. As in, if you're not just using the type, like you're actually making colors like this, then we just need to get rid of it. WebGL2 is a library that talks to the graphics card. It's fairly portable in 2026. Quite a number of devices support it. There was WebGL1, which is more specific and doesn't have as much power as WebGL2 does. But yeah, what we want to do is we want to ask the browser for a WebGL2 context. If it's null, that means that it's not supported on the device. So however you want to do it, I just put a nice helpful message that says to the person, hey, you know, it failed to start. It's going to put it onto the screen. And then it's also going to throw an error, and this will stop the code and it'll put it in the terminal, that same message as well. Now, when building this, I found it very useful to just have this available globally. Let's come over here and let's go to Visual, and we're going to create a gl.ts file. Again, I'm going to add a lot of comments just so that it's, you know, can help describe what's going on. But basically, this is going to be the one sort of WebGL context that we have for the whole application. And we can set it, and then we can also get it. And through our rendering code, we'll probably call this get GL function a lot of times to just get WebGL. This will make it a lot easier. You don't have to do this. You could pass it around, but I just find this a lot easier. Let's now go back to visual.ts. And now that we have it, let's come over here and we'll do set GL, and we'll say our GL context that we just got. So now the entire application is going to have access to that WebGL context. In order to support transparency, which we'll need later, we want to enable it. So we enable the blend mode. And then this blend function is how we actually do transparency. So source alpha means that we're going to use the alpha of the color. And then 1 minus source alpha is just how we compute that. There's a bunch of different modes. You could play around with them, but basically what this means is that something that is 1 of alpha is going to be fully opaque. Like it's going to, be solid and you won't be able to see through it. And then anything that's less than 1 is going to start being transparent. We're also going to enable depth sorting. So this will allow the graphics card to determine for us what is behind what, but it needs some context. In OpenGL/WebGL, it actually basically smashes all of the objects in the whole world into a box. And this box is basically -1 by 1, -1 by 1, and -1 by 1 into this cube. So basically, we're just going to say the clear depth is 1.0. This doesn't mean the whole world is that way, but when we actually take the world and then render it on the screen, it'll be that size. Don't forget this one. This one actually enables the depth testing itself. And last thing, the graphics card needs a way to actually determine whether something is ahead of something else. So basically what we're saying here is we're saying if an object is less than or equal to, then it passes the depth test. It's able to actually be drawn on the screen, if I understand correctly. So the reason why less than or equal to we can use this is because if something is less than, then it means that it's closer to us, if it's less than in the distance. Or we'll also do equal, which means that if we end up drawing something later and it's like equal in distance, we want it to win, right? If we draw a path or something. Now in actual practice, even if you do this, you can still have Z fighting, which means that if an object is exactly at the same spot, then it may be very difficult for the graphics card to determine which one actually wins. But either which way, this can kind of prevent some Z fighting compared to the other methods, but isn't perfect. Okay, let's actually build the function that is called every frame. So all of this we want to set up and not call every frame. A lot more efficient to just set it and do that. Now, if we need to switch, sometimes there is reasons why you want to call it each frame, and maybe you have it and then you switch the function or whichever. But we'll do it without doing that. It's more efficient not to do that. We're going to get a handle to our WebGL by just calling our getGL function. And you're going to see a lot of this where we can just call this anywhere in the program and getGL. We're going to tell WebGL what color that we actually want to clear with. So we're using our clear color and passing in the values there. And then this is the function that actually performs the clear. So what we're doing here is we're telling WebGL that when you start a frame, because we're calling this at the very beginning of draw, we want to clear all of the colors there with this color, right? So we want to just throw a big paint bucket over the entire computer monitor or, canvas, right? Because it's only going to draw here. And we want to clear all the colors out. We also want to clear the previous depth information. So as things are drawing, because we have our depth test, what the graphics card will do is it'll actually keep a buffer of the objects that are in front, or just if there was an object that drew there, and what distance it was for each pixel. We want to clear that out as well. And it takes bits. Basically, these are ones and zeros. And because WebGL is a translation from just like C library, it uses the same thing. So what we want to do is we want to set the color bit to 1, and then we want to set the depth bit to 1, and everything else is going to be 0. There's actually other buffers, such as the stencil buffer, that you can use, but we don't need that right now. The stencil buffer you really want to use only for certain effects. We don't care right now. And then our next step, which we'll do in a second, is that we're actually going to draw everything. You don't have to write this, but this is, we're going to put all of our draw stuff here. Okay, now that we've coded this, let's now go back into main TS in the engine, and we'll come back to our engine class that we did earlier. Starting off, we'll import our visual that we did, and then we'll keep a reference of it for the engine. Again, static, meaning it's shared through the whole application. In start, at the very beginning, before this loop, let's come over here and let's say engine visual equals new visual. And this will create a new visual engine. Inside of the loop, what we're going to do is we're going to call our engine.draw function. So this is going to call this. In fact, let's make this, I made a mistake. Let's make this private. Okay, and then what we're going to do is we'll say engine visual dot draw. So this is actually going to draw the engine code. And then finally, while we've coded everything in our engine, we now need to attach all of this to our game. So let's now go to game main.ts. Let's get rid of the previous console.log that we did. We're going to import our engine, and then we're going to start our engine. And if everything worked correctly, you should have this really small blue rectangle. This right here is the canvas. If you've done everything from this point, WebGL2 is now set up and it's rendering. If you see a message here that says WebGL2 is not supported, then it may not be supported on the device that you're using. You can also see this error if you inspect and you go in the console. But on this device, it is supported, so we don't see the error. Okay, you might notice that the canvas is incredibly small. And to be honest with you, the canvas doesn't have to take up the entire page, right? If you go to somewhere like itch.io, right, the game is only on this, little thing, and you can see all the other buttons and the header that, can explore other games and stuff. So you can make this as big as you want. But I think for this development purpose, we'll come in and we'll actually make this take up the entire screen. And let's do that with CSS. So let's come over here into our game, and we're going to create a new folder, and we're going to name it assets, and we'll hit enter. Inside of this folder, let's come over here and we'll create a style.css. You might notice that there's these little margins on there. So let's get rid of that. Let's come over here, body margin 0. And then you'll notice that we need to actually wire it up. Let's go into our index.html. You might be able to just type link here, and then there's a CSS. What we actually want is we want to do our assets and then style.css. Yeah, and if everything worked, the little margin, the gutter, should actually be gone if we add this to our index.html. Let's go ahead and let's jump back into style.css. And then what we're going to do is we're going to set the canvas to 100%, and we're going to set the width to 100% of the view height, this VH here. And then it should stretch out. You really can't do 100%. I'll show you what that does. Yeah, so see how it doesn't actually stretch? This is because the body is sort of itself is stretchy. And anyway, one of the easiest ways to do this is just do VH. Now, you can adjust this if you don't want it to take up the entire web page. Maybe you want to put other things on the web page. So you can play around with this if you want. Perfect. With that being said, we see the entire web page here is taken up. Now, this is a great foundation. Now we're going to code our graphics engine. Okay, we're actually hitting one of the most difficult parts of this whole process, and that's getting triangles to draw on the screen. We're going to add some code to get billboards working. But if you run into any issues, what I would do is just say that all of the code is in the description below. Just have a look at your code. Just make sure that as you're typing things in, just be very careful. And also too, don't feel bad if you end up, checking out the code from the description below. Or if you, ask questions to AI. AI is incredibly good at debugging graphics things. Graphics things are notoriously hard. Harder than testing a lot of other things because multiple things could be going wrong. But once you actually have something drawing on the screen, then you can confirm that like your camera works, and you can confirm that the renderer works and that there's not errors and things. But just don't feel bad if the first time around it doesn't draw. This is probably one of the more difficult things to actually do. Once you get something drawing, it all becomes easier from there. Let's now come to our visual.ts file, and we're going to go all the way up to the top, And right before visual, we're going to add an interface for a drawable. Now, a drawable is just some object that can be drawn, and it's an interface, meaning that it could be any class that you want, but it has to implement drawable, and then it has to have these functions. Okay, so now let's come over here into our visual, and let's just go ahead and add a set of drawables to our visual class. Go ahead and scroll down to our draw function here, and we added this nice to-do here. Let's go ahead and we'll add the drawables loop for that. So we'll loop through each thing that's visible, and then we'll call its draw function. Very important that you do this after the clear, right? Because this is where we throw a paint bucket over the whole screen, the canvas, and then after that we can draw on a nice clean canvas. Take a look at this second curly bracket here. What we're going to do is we're going to add two other functions here, a register function which says, hey, draw me please, and then an unregister function which says, okay, stop drawing me. From here, we need a place to define actual objects in our game. So let's create a world manager. Let's create a folder called world. And in here, what we're going to do is we're going to create two files, world.ts, and then we're going to create another one called entity.ts. An entity represents a single thing in our world. And that entity can have components. And one of those components, for example, can be something that can be drawn to the screen, for example. Another component might be the location of that entity. Let's create two classes. So we'll create a component class and an entity class. An entity has components inside of it. A component will have a reference to the entity that it's a part of. And then it will also have an onStart and onEnd function, which is nice for setup and cleanup. You might have watched my Python series where we implemented an entity component system there as well. And in order to do this in TypeScript, we need a way to determine the type of things, right? And just say, hey, get me the location on this entity, or get me the terrain on this entity or something. So the way this works in TypeScript is when you create a class component like this right here, this component here has a constructor or on it that can do something like this. So in other words, if I create a class called orange, I can do this. I can say new orange. Essentially what I'm saying here is this is a type that has a constructor. It must have a constructor that creates T. This will become a lot more apparent when we use this. Let's go ahead and we'll create a map of all of our components. We're going to only have one component of each type just for simplicity. And again, this is kind of like our type definition. We can actually store a reference to the constructor itself, which can help us to distinguish types. This is just how it's done in JavaScript, and TypeScript carries this out. And then we'll actually have the concrete component itself. Start off by creating these functions here. So we're going to be able to add components to our entity. We're going to be able to remove them. We're going to check and see, oh, does this object in our world have a particular component? And then this will actually get a reference to that component. So we can just say, hey, get the health of the component, or get the location of the component, or whichever, and return that. It can potentially return undefined if we don't have one on there. The has function is pretty straightforward. We just call our map, and we literally call another function called has on it, sending the kind there. Now, again, this is where we're passing in our constructor. So you'll be able to say, does object have a location, for example, and location is a class. The get is also very straightforward. We're just going to call get and then just as the type, not as component, and return that. Now, add is where it's going to get kind of interesting. So first, we are passing in a component, not a kind or type. So what we do is we want to get this kind here by doing this. We're getting every single object in JavaScript that is an instance of a class actually has this dot constructor, which is the object prototype constructor. This object is the class name. So we're getting that as our nice type that we created earlier for that. If we already have a kind of that thing, then we're just going to throw an error that we already have one. We're going to set up the component by telling it that we are its entity that it's being added to, and then we're also going to set it to we're going to add it to our components. Now this is a nice function where we can call onStart, where the component itself can set itself up or do any sort of logic it wants to, and then we're going to return the component. This is helpful for if we create it and then we want to do more things with the component later. Okay, and then let's go and we'll do this remove function. Now, I want to be more lenient with the remove function. We'll try to get the component. If we don't have it, we'll just return. We're not going to throw an error saying that we don't have it, because we might want to call this just to clean up, and maybe it's, oh, it already was cleaned up or something. This is just nice and easy on that. And then pretty much kind of the opposite of what we were doing in the add function. We're going to call the onEnd first so that the component can do any breakdown that it wants to do. And then we're going to call this, it's just set to null, and then we're going to delete it. Now that we've done all this, we're going to add one more function, which is just going to be nice and convenient later. And that's the clear function. So this is kind of like doing remove, but not just on a single component, but doing it on all of them. So we can just clear a component out if we want to. Okay, now let's go to world. So let's go to world.ts. Let's import our entity, and we don't have to import it as a type, but this will be more proper because we're just using component as a type. And then let's go in here and we'll add an interface for something that can be updated. This will be helpful later on. And this has an onUpdate function. This is different from drawable because this is the logic or something that's being done. It's good to distinguish between these because we can update all of our physics and our game logic and everything, and then we can draw everything, right? So that there's not things going on in the middle or things are not jumping around weird or that sort of thing. In order to organize all of the objects in our game, let's create a world class, and then we'll add a set, and then we'll have a list of entities that are in the world, all of our objects, and then also a separate list for anything that we want to call the onUpdate function of. And this is nice and efficient as opposed to giving all the components an update function or something. This is just really nice because we'll only call the update function if the component asks for it. Now you have the option of just doing new component, for example, but this is a nice function here that can just also make an entity, add it to the world, and then return it. And we'll probably be using this nice convenient function for a lot. And you know what? I forgot something. I forgot to do the actual constructor for the entity itself. Do me a favor, go into entity.ts. I'll tell you, it is so easy to make mistakes on things with all this. Find the very top of where it says entity here, and we're going to come in here, and let's add a nice constructor to this. So the constructor is going to also take in a bunch of components that we can start with. This is just for convenience, so that we don't create an entity and then we have to call add all the time and stuff. Let's just add it like this. We'll add each one of them first. And we're going to call false so that the components don't call their onStart function right away. Let's add all the components there first, and then we'll let all the components call their onStart function. This is beneficial because there might be a component that needs another component, like our visual component might need to know where the object is located, like the location. Okay, now let's go ahead and go back into world.ts. And now the error is fixed. Perfect, perfect. The last thing that we want to do is go to the end of line 22. And what we're going to do is we're going to add, right inside this curly bracket, we're going to add an update function. And this update function is simply going to take everything that has said that it's updatable, and it's just going to do its onUpdate function. Perfect. Let's now go ahead and let's go into main.ts of the engine. This is where our engine class is, and we're going to add some things to it. The problem that we have is that when we start the engine, the code is going to just be consumed by this loop. It's never going to be able to get out of this loop until the game is over. So we need some way to be able to call some code after the engine is all set up. And we can create a nice callback by doing that. Find where it says the start function, and let's go right inside of these parentheses. And we're going to add a setup function that we can call. Go to the end of this visual. Once everything is set up, we're going to come in here and call this onSetup. And this is going to allow somebody when they're making a game, after all the engine code has been set up, to then call some, do some code for actually, loading the game and that sort of thing. I feel like in another video, we're going to change this later to a stage system, similar to what we did in the Pygame series, but this is good enough for now. Next, we're going to add a reference to our world, and we also need to import that. So let's come in here, we'll do import. I forgot to do the hit enter, so let's do that. Yeah, so now we've got a reference to a world, and we're going to create a new world. So we're going to say engine world equals new world. Let's go ahead and we're going to make another function for updating the engine. So we'll come in here, we'll do private static update. And what this is going to do is it's going to update the world. So it's going to, every one of the entities that are updatable or components that are updatable, it's going to update all of them. Let's go ahead and let's do engine.update and make sure that you do it before the draw. One of the reasons why is because we want all of the input and physics and stuff to apply, then we want to draw. It'll make it look a lot more responsive. If you do it the opposite way, if you add update after, then things might seem like they're lagging when they're really not. Let's go ahead and actually test this code that we've done. So let's go into game and then main.ts. And you might notice that there's now an error here. And this is because we need some kind of function. Let's come over here and let's add parentheses inside the function, add a little arrow there, and then let's do our curly brackets and go from there. So the curly brackets, this should all be inside of these bigger parentheses here. Come over here to line 5. Let's create a class called eggs and we'll hit enter. So what we're going to do is eggs is going to extend component and it's also going to implement updatable, right? So updatable was that that interface that we created earlier. Type is good here because it's an interface. Now, you might notice that now there's an error and that's very good. It's basically saying that eggs must have an onUpdate function because it's now implementing updatable. Rightfully so, because when we add eggs to our world, then we're going to do that. Let's come over here and hover over here. There's actually, you have to kind of sneak up on it, but you can do quick fix. And there's this nice screen where you can say implement interface updatable and hit enter. If it doesn't do it, you can also just type this out as well. And it's really cool because it creates a nice error here that says the method is not implemented, which is nice because then when you're ready, you can implement it. Let's do that now. Let's come over here and let's do a console.log and we'll say I am doing something. And there we go. Okay, now let's actually use this component that we created. The way that this works is we'll say let entity equal, and we'll say engine.world.makeEntity. And then we can do that. Now, we don't have to specify any components. We can just have an entity that's completely empty, and that's fine. But let's add our new component that we created. So let's say new eggs and do that. Now, eggs is updatable, but it needs to be able to add itself to the update function. And I think that this is a good practice, the way that we're doing it, because it's just more efficient. We might have components that aren't updating. Come over here to line 14, and we can start typing on start. And it's a nice function. And then what we'll do is we'll say engine world.updatables.add this. Basically saying, hey, I am updatable, call my update function every frame. And then we're also going to want to clean up after ourselves. So on our onEnd function, we're going to come in here, we're going to say engine world updatables, and we're going to say delete, and we're going to say this. Just to let you know, you don't actually have to do this, but you can use the entity later, and you can do stuff like has, and you can say eggs, for example. Right? So check out how we're able to just use the class because of all that secret sauce type stuff that we did earlier, right? We can now just type this in and we can get, has eggs, and it's a Boolean value that we can just say like if, has eggs, and we can do some logic there. We don't actually have to do that, but I'm just kind of showing you how you can use it. Okay, let's test that this actually works. So now I have to find where my window is. Let's see, we have a slight error here. Oh yes, this is good actually, and it's good we're hitting this. So we can't actually access eggs because we're using it earlier than we are. So let's come over here and let's take this whole eggs class and we'll put it up here and then it should work. Yeah, there we go. Then that's good that you saw that because the class itself just needs to be declared before we actually end up using it. So in the terminal over here, in the console here, what you can see is that we're actually doing something and the number is growing. And that's because I have a setting on where it just consolidates all the messages. But yeah, it's getting bigger and bigger and bigger because we're just calling it every frame, right? By the time I've been talking, look, it's already called it 2,000 times. So this is good, it's working. Okay, let's go ahead and close this. For cleanliness, I'm gonna go ahead and delete our the eggs class. But you don't have to, you can keep it if you really want. And then because of that, I'm also gonna delete this. Okay, so we have a really nice clean engine start function here that we can put code in later. Now that we've set everything up, what we're going to do is we're going to build our graphics engine, and then we're also going to create components for everything. So let's come over here, let's go to Engine, and we'll create a new folder called Components. These are going to be common components that you can use in your games. By the end of this video, we'll have a billboard component and a terrain component, which you can then use in other games as well. But also for the game that you're creating, you might have specific components created for your game. Like in RPG, for example, we might have a nice enemy class and combat and things. Maybe that goes in game and not the engine. For this video, we're going to create 4 files in our components folder. So let's come over here. We'll say billboard.ts. We'll say flycamera.ts. We'll say location.ts, which we'll do first. And then we're going to say terrain.ts. It's nice to add these to the engine because then you can use these in any game that you want. Now, in visual, what we're going to do is we'll add our graphics code as well. So let's come over here. We're going to add camera.ts. Go ahead and add material.ts. Go ahead and add mesh.ts. This is going to be our geometry. Go ahead and add shader.ts. And finally, go ahead and add texture.ts. Now we have all the files stubbed out. First, let's go into location.ts. Let's go ahead and import the following. So matrix 4, quaternion, vector 3, and then component. Go ahead and make a location class. Now, location is going to store the 3D orientation of an object in 3D space. And basically we can represent objects by their position, how they're rotated, and then their scale. These are various ways in which you transform the object. And these 3 are very standard in working with 3D. There's actually more like shear and reflection and all these different things. But these are the kind of 3 fundamental transforms that you would find in 3D. We're going to store these here. So position is a vector 3, meaning that a vector is a list of numbers. So it's X, Y, and Z, right? So we have a vector 3 for 3 numbers, X, Y, and Z. A quaternion is 4 numbers. 3 of them are actually imaginary numbers. There's some secret sauce to how this works in math, and I don't want to get into it in this video, but a quaternion can be used actually to store the rotation of an object really, really well. And it's not susceptible to something called gimbal lock. There's a fantastic video that somebody does where they actually explain kind of how quaternions work, which I'll link in the description below if you're interested. But basically as far as this video is concerned, just know that quaternions are really good at storing rotation. And we're going to use the GL matrix functions for manipulating this quaternion. And finally, scale is how big something is. And we have, it is a vector 3, so we can scale it with X, Y, and Z. If you're not familiar with a matrix is a 2-dimensional set of numbers. And in 3D graphics, we generally use a 4x4 matrix to transform things or to do some kind of operation on a vector 3. This is a whole concept in math if you ever take linear algebra, but basically how it works is that we can take these operations here and then we can create a matrix out of it. And by taking input and multiplying it by the matrix, you can actually perform all of those operations very efficiently just by one operation. In fact, matrices are so powerful that you could store hundreds of transforms inside of one. And then just, multiply a single vector by it, and it's just one operation. Very, very efficient. We'll come over here and we'll create a constructor for this. We're going to feed this with defaults for everything, but the position will be first in case the user wants to specify a specific position. This will be the most common. And then if they want to store, do a rotation and scale, that might be less common, but we'll still allow them to do that. And then it's going to set those variables. We're calling super because this is a component. So we want to call the constructor of the component. And then we set our matrix to identity. An identity matrix, when you take a vector and you multiply it by that matrix, an identity matrix does nothing. And so it's basically just nothing. But this will change later as we update it. We want to sort of protect our matrix from being changed because we're only going to calculate it in this class. So let's create a getter for this, not a setter, for getting the matrix. I like to put private things with a little, what is that thing called? Underscore. And then anything that's public, I don't do that. But of course, you can choose how you want to do it. Okay, this is where we actually create the matrix. We'll refresh it into an identity matrix. We actually don't need to do this, but we'll do it anyway in case we add more things to this function later. And then what we're going to do is we're going to take the position, rotation, and scale, and then we're going to make a matrix out of it. This is going to allow us to take the geometry, like a model or a terrain or whichever, and take all of the points of that geometry and multiply each point by this matrix. And it's a very, very efficient way of just applying a rotation, position, and scale to a model in 3D. Now, what you'll notice about all of these GL matrix functions is that the first thing here, for the most part, is actually the output. So instead of returning things, the first thing here for the first argument here is going to actually be where it's returned into. There's a massive reason for this. It's because we don't want to create a new matrix every single time. We want to recycle the memory. I highly recommend that you use these linear algebra libraries for doing this sort of thing. You can obviously write your own if you want. It's a good practice if you want to learn the math behind it. But people have been writing these libraries actually for decades and decades and decades. In fact, linear algebra is probably one of the first things that people got computers to actually really do, in the grand scheme of things, because it applies to so many different things in 3D space and computing numbers and all these different things. And these libraries are massively optimized by by 2026. So I highly recommend you use these. But yeah, so anyway, what we're doing is we're applying this rotation, position, and scale, and we're putting it into the memory here, into this matrix. Okay, now that we've done this, let's go ahead and jump into the visual stuff. Let's go to the camera.ts. For ease, go ahead and import the following. Let's create a camera class. A camera is going to allow us to take all of the objects in our 3D space and move them into a place where they're going to be on our computer screen. So we have a 3D world with a bunch of objects all over the place, and we need to somehow draw it onto a rectangular computer screen. And so this camera class is going to help us to do that with matrices as we used earlier. So we have two matrices with a camera. The first is a view matrix, which positions everything as if the camera was the center of the universe. So the camera may be somewhere in 3D space, it may be at some X, Y, and Z coordinate. But after the view matrix is applied, the camera is now 0, 0, 0. And everything else is moved in, where it would have been as if it was with the camera. This actually simplifies everything greatly because then we don't care where it was in the 3D space. We only now care where it was relative to the camera. The projection matrix gives the camera a lens. And this is important because we need a way to be able to take all those objects and say, how is it going to fit on a rectangular screen? So eyes are actually spherical. And because of that, things that are further away from us are actually smaller. Because they're spherical like that, we can actually see a much larger range of things. It's just that when things are further away, they're a lot smaller. This is called perspective. And perspective is a kind of projection. Another kind of projection that's very common in video games is orthographic, where objects are always the same size, no matter how far away they are. And that sounds really strange, but if you've ever played a two-dimensional game where there's tiles and characters and things, that is a perfect orthographic, perspective, because if the character moves further away or closer to the screen, they don't actually end up getting smaller in a 2D game. But in a 3D game, we have perspective where objects do get, smaller or that sort of thing. Actually, you can have 3D and orthographic, but we're going to do perspective from here. This nice location class that we coded, the camera also has a location. We're most interested in the position and the rotation of the camera, and we just ignore the scale. And then this right here is going to be the output matrix of actually the location, which we did, and then the view matrix and projection matrix. Now, the reason why I'm adding these, and this we'll actually use later, but we want to recycle memory as much as possible in JavaScript and TypeScript because it has a garbage collector. And so we're just going to define these here, and then later a function that we're going to use will actually end up using these variables. It's actually very important because if you just make new vectors all the time, then you're going to pile up with garbage that's being thrown away, especially every frame, because every frame it's called 60 times a second. And then the garbage collector is going to be all, have a ton of garbage it has to clean up. And then you'll end up getting these weird kind of, just lags all of a sudden in your game. To avoid this, let's go ahead and we'll predefine these. Let's go ahead and create our camera. Now this is going to be protected, and we're going to have child classes of this camera. One of them is going to be perspective camera. But either which way, let's go ahead and do that, and we'll define we'll just set these up here real quick. Now let's go ahead and define the rest of the functions. It is a drawable thing, but we really don't need to do any setup or breakdown for the camera. It's just used as we use it, so we can just ignore these, but go ahead and do put these. And then in our draw function, we're going to call two things. We're going to refresh the view matrix, we're going to refresh the projection matrix, and then we're going to bring everything together into the camera matrix itself. And this camera matrix can be used to multiply parts of geometry in the 3D world so that it's oriented in a way that fits on the screen. And obviously, if the camera wasn't looking at it, then it's going to be off the screen. We define an abstract function here, basically saying that if we have a child class of this camera, it must have this function here. It must have a way of doing or refreshing its projection. But the view matrix is going to be the same regardless of what camera that you have. As you'll recall, the view matrix basically makes everything as if the camera is the center of the universe. So what we need to do, there is an equation that we can use to calculate this, and it takes the center where the camera is, it takes where the camera should be looking at, and then it also needs to know the up vector of where it is. So it needs to know, okay, yeah, I'm looking at this, but how should the camera be rotated, right? So where is up? So we need to figure out what is in front of us, where the camera should be, and what is up. Let's go ahead and set our forward vector that we defined earlier. And the z coordinate is 1, right? So what we're saying is that x is left and right, and y is up and down. Z is forward and backward, right? We're in 3D. So 1 would be in front of us, and -1 would be behind us. This is where we're going to use our quaternions. And again, you don't have to understand what a quaternion exactly is, but one thing that you should know is that a quaternion basically rotates a vector. A vector is kind of like a direction, and then what we're saying is, okay, the forward direction, now do it based off of this rotation. So maybe the camera is facing west, so we want this forward vector to face west, essentially. So it's going to rotate it so that it faces west. Now the vector might be all the way in Antarctica. So what we want to do is we want to add the position of where the camera is to that forward vector to be able to determine where it is, right? The center of the camera is going to be somewhere in Antarctica, and the target is going to be a meter ahead of that point in Antarctica, right? So we want to add this, position where it is to the forward vector, and then we're going to output to this target here. Calculating a view matrix is a solved problem, and pretty much every linear algebra library has a function for it. So we're going to do a lookat algorithm. If you take your hand, for example, and you point with your index finger, and then you take your middle finger and you go like this, and then you have your thumb go up, That's basically what a look at is doing, right? So it's basically saying like this right here is my Z, and then this is X, and then this is up. Basically, this look at algorithm is essentially taking this target here. That's our forward, right? That's what we're pointing at. This up is where your thumb is, like it's going up. And then the position is the center. We actually don't care about Z, but I just wanted to say we don't care about X, which is left and right, but I just wanted to say that just so you also know that it's figuring that out as well. Yeah, and then it will output it to this view matrix. Final thing we're going to do for our camera before we go to the perspective camera is we're going to do a public getter for the matrix. We don't want to set the camera matrix. We want the camera to compute its own matrix, but we will have a function to get it. Now, the way that we actually use this camera is that we do the following. So we create a subclass of camera. This will be a perspective camera. Maybe we'll make an orthographic later, but again, perspective is a type of projection where objects that are further away are smaller. Because we're trying to ultimately get this to be on a computer screen, we need to know the aspect ratio of the computer screen. We need to know, okay, how big, based on width and height, what's the orientation? Again, please don't feel like if, with the comments, you have to copy all of this. But field of view is basically the angle of the left side of your vision to the right side of your vision. Now, human vision is actually quite large as far as its field of view, especially because you have two eyes that can, span from left and right. And if you close one of your eyes, then your field of view becomes, less in that direction. But you're not going to be, your face is not going to be right in front of the monitor unless you're doing something like VR. So because of this, for just a regular computer screen, I think that 80 to 100 degrees is generally a good value for this field of view. Now, I will say also that like pro gamers and stuff, they'll increase their field of view so that they can actually see people, way over to the left or way over to the right. But for general kind of practice, it's not the best experience for most people. It can actually make people motion sick if the field of view is off. So 80 to 100 is probably a good, sort of value to set this to, but we'll support whatever they put in there. The final thing that we need to do is determine how far objects, are that we can draw. And this is with the near plane and the far plane. Now, the near plane is the closest distance that something is visible. And that sounds silly, but in computer graphics, the way that a depth function works is that it actually needs to have some kind of minimum, and that minimum not be 0. And there's reasons for that too. Let's say that, for example, like, I don't know if you've played these games where it's like third person and then you can zoom in and now you're in first person, like Skyrim or, World of Warcraft or something. But at a certain point when things get really close, we actually want them to disappear. Like you might notice that your player disappears after a certain point. And that's the near plane. And actually a value like 0.5 or 1 is actually quite good for this. The higher you can generally make it, the better that the depth, sorting is actually going to be. It's just going to be more accurate. And I think that 0.5 is probably an appropriate number for this. The far plane is your view distance. I think 200 is fine for now. For increasing it, you'll actually also need to increase this slightly as well. Otherwise, your depth function is going to be gradually less and less accurate. Okay, and then let's go ahead and actually create a constructor for this. We do require the aspect ratio because we have no idea how big the canvas is. But the field of view can actually be optional. And I think a good default is 85 degrees. And then again, perspective is a solved problem. So we're just going to call map for perspective. This is the output. This is the memory in which it's going into. We feed our field of view into here. Now we're actually converting it to radians. And radians is a nice unit of measurement instead of degrees around, an angle or a circle, where 2 pi is fully around a circle. To convert it, you just multiply by pi and then you divide by 180 to get, to convert degrees into radians. But degrees is probably better to work with as a human, and then, but the actual equation itself needs radians. We'll pass in the other things too as well. Okay, so now that we've done the camera, let's go ahead and I think the next part that we can start with is the shader. So go ahead and go into shader.ts. We're going to use WebGL for this, so go ahead and get it. So a shader is a program that's executed on a graphics card. A graphics card is this massive parallel processor that has tons of little processors that it takes a massive amount of work and it breaks it up amongst those processors. And then, they all work together to accomplish some goal. So take a 3D model, for example, that has a tons of different dots or vertices. We need to actually process each one of those dots and move them around to where, relative to the camera, and be able to move them where they need to be on the screen. This kind of operation is done in a vertex shader. So it's a GPU program that takes in a bunch of dots and then outputs really a bunch of dots. A fragment shader is a program that essentially works on pixels, right? So it's a program that's executed per pixel. The reason why we call it fragment is just fragments are more generic. So the idea was that we could also output to a printer, or we could output to some generic data or something that's not pixels. So they decided to call it fragment, I think. But yeah, it's a more generic term. When we actually draw everything to the screen, we will have a vertex phase where we take our geometry and move it and do things. And then we will have a fragment stage where we actually draw all of the pixels there. How do we get the code from a file to the graphics card? Well, let's create a nice class that will tell us what kind of shader it is, whether it's vertex or fragment, and the actual code itself in a string. We'll create a nice constructor for it. And then just for context, for WebGL2, we use a language called GLSL to write our shaders. And we made a really nice thing up in shader type that lets us do that. But WebGL itself actually needs these values. So we'll just create a nice conversion function that converts our types into the ones that WebGL wants. And then just to be exhaustive, we'll also do that as well. There's actually other types too. There's compute shaders if you want to just do generic computation, and all sorts of geometry shaders and stuff. There's all sorts of other kinds of shaders, but this is good for now. So let's create our actual class that's going to send our code and all the stages, vertex and fragment, over to the graphics card. We're going to create a WebGL program. So a WebGL program is a program that is executed on a graphics card, and it includes all the different stages. And you can add one stage, or you can add 2 stage, 3 stages, whichever. But generally speaking, for doing graphics, you'll have a vertex stage and then you'll have a fragment stage. We'll create a list of different stages that we're going to do from our class that we created earlier. We'll make a nice constructor that takes in these stages. Now, it doesn't load it at this phase, but it will load it in the setup phase that we do in a second. Let's go ahead and actually create a setup function that we can call later to actually do the send it to the graphics card. We'll go ahead and get a handle to our GL. We'll call WebGL to make a new program that has nothing in it yet. And now we need to compile each stage. So let's make a really nice function here that just compiles each stage and gives us a WebGL shader. Okay, so then for each stage that we do, we'll have the shader that we do, which we'll do in a second. And then we just need to call GL attach shader, which attaches it to the program. And then we return the shader. We're going to get a list of shaders. There's a reason why we're getting a list of shaders, because then we can clean it up later. Let's jump into this function now, and we'll do the logic of actually compiling everything. Let's go ahead and get a handle to WebGL. And then we call GL create shader, and we get the type. So we're saying, hey, create a vertex shader, or create a fragment shader. If this failed, then we want to fail loudly, and we want to throw a new error. These two functions send the source code for compilation, and then actually compiles the source code. Now, sometimes you'll see tutorials skip this part. This is massively helpful if you have errors in your shader, to have some really nice logging and information that you can use to then fix the shader later on. So we'll get, we call this, if the compile status is not good, like if it returns 0, then what we'll do is we'll get the shader info log to see what happened, and then we'll output it so it's nice and loud, and we can fix the shader later. Otherwise, if everything went good, we'll just return the shader. Now, let's go ahead and scroll up to this setup function that we did earlier. We need to actually do the linking phase so that everything is linked together. This could also fail, so we need to handle that. And so similar to what we did with the if it fails to compile, we also will throw an error if it fails to link. And the function is very similar. So instead of, what was it? It was get shader info log. We're going to call get program info log. By the way, many of these functions that we're calling are very similar to actual OpenGL itself. And so if you learn this, then it's going to be very, you can then learn OpenGL and see a lot of the same functions, basically. This phase is optional. You really don't have to do this, but this is proper, procedure is to actually clean up the code that we attached. The reason why is because, okay, the code is already compiled, it's already brought into machine code, and the program is linked and everything's good to go. We still have, in addition to that, the source code attached as well, right? It's just hanging out there in GPU memory, and we don't actually need to do that. So in order to do that, we detach shader, which was the opposite of this attach shader, right? And then we go ahead and just delete the shader. This doesn't actually delete the shader on the program. The program already has a linked, source code and everything. This doesn't actually delete it on the program, but it deletes that additional attached shader that we needed to have and cleans everything up. Cool. Now this loads the shader. So let's add a couple other different functions to actually use this. The bind function we're going to call to use the program. So when we want to draw, for example, a tree, we'll say, hey, we have a certain, graphics program that we're going to use to draw the tree. And so this bind function says, hey, use this program for the next draw call that we're going to do. And then likewise, we also have a function that just cleans up the program and cleans up the memory when we're ready. Finally, scroll down to the very bottom, and let's just also add a nice function that just says, hey, is the shader set up? We're kind of doing this a little bit lazy, and this is beneficial because we can define our shaders, and then when we're actually using them, it gets, compiled and that sort of thing. This is quite a bit of code. I'll just remind you that all the source code is in the description below if you ever get stuck. Okay, so let's come over here and we're going to go to mesh.ts. Like the other ones, let's get our reference to our GL function. And then so this file is going to define the actual geometry. And we could potentially have two different types. We could have integers, and much more commonly, we could have floats. Create two classes. We're going to create a vertex attribute class, and we're going to create a mesh class. So the way that this works is that for a piece of geometry, a mesh, right, we have a bunch of dots that make up an apple or a character in a video game or a tree. And each one of these dots are used to make up a bunch of triangles. Each one of these dots, they store the position of where they're actually at most of the time, like 95% of the time, they'll have some kind of a position. But they could also have other kinds of information too that's helpful as well. One example is we can actually have a bunch of colors for each dot, right? You could just, for each little point, you could actually store a color value there that, tells the color for how it is. You could store if you have a texture, like you want to put an image on top of the mesh and kind of do that, you could store what parts of the texture should be at each point. Those are UV coordinates. You can store normals are a point that extends outward from the mesh, and it helps with calculating the lighting at that particular location. So there's lots of different attributes, and the way that it works is that for each one of these attributes, like position and color, we're going to have a long array of numbers for those values, right? So for example, and what you'll do is you'll have, for positions, we have X, Y, and Z. And then the next dot is going to be right next to it, and it's going to be X, Y, and Z. And then it's going to be X, Y, and Z, right? So our array, for example, is going to look something like this, where this has 4 dots inside of it, right? You see this is the first one, this is the second one, and this is the third one for 4 vertices, right? Vertex for plural. Each one of them taking 3 numbers for the position. Now, different attributes, so each attribute has a list like this. So for colors, for example, it's probably going to be RGB, 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 right? You're going to have you know, these numbers right here, these numbers right here, etc., right? For UVs, you're only gonna have 2 each, right? So it might be UV, 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 right? A number here, number here, number here, number here, right? For the first one, second one, third one, and fourth one, right? So first, let's define an array of numbers like we just talked about. And then we're also going to define a vertex buffer. This is the actual reference to the memory on the graphics card, a WebGL buffer. It could also be null if we haven't buffered it to the graphics card yet. And then just like we talked about, for each one of these attributes, we're going to need to know how many numbers are in a single vertex. So for position, we have an X, Y, and Z coordinate. So we would have 3 elements per vertex, right? X, Y, Z, X, Y, Z, X, Y, Z, and so forth. And finally, we don't have to just have floating point variables, which are variables with, or numbers with a decimal point. We could also have integers. There's other types that you can have too if you want to do really fancy things, but 95% of the time, you're just going to use floats. And graphics cards are optimized to use floats anyway. Let's come over here and create a constructor that puts all this together. So we're taking in the elements per vertex. This is required, but we can also optionally allow you to specify the data, or you can specify the data later as you're building it. Now we have this nice array that we talked about, but we actually need to get it from the CPUs and the RAM over to the graphics card. So this is the function that we're going to do that. Get a reference to WebGL. And then we're actually going to call delete right away. This is harmless if you haven't actually buffered anything yet. The reason why is because this is not just sending it to the graphics card, but we could send it to the graphics card again if you want, right? A game like Minecraft, for example, like you break a block or something, well, it actually sends the world geometry back to the, another copy back to the graphics card, or it modifies it somehow. What we're going to do is we're going to delete the old mesh and we're going to create a new one. This will let us modify the mesh later. Tell the graphics card that we want to make a new buffer of memory on its memory. The way that WebGL works is it has these sort of names for things when you're currently using it. So essentially you're saying, okay, I'm putting this buffer in focus, right, as the current array buffer that I'm working with. And then for the thing that we put into array buffer, we're now going to buffer the data. So we're going to create a new float 32 array of the data. So this actually tells the graphics card what kind of memory we want it to be in. And static draw is the fastest kind of memory, but we cannot modify it. So we're saying send it to the graphics card. I don't want to touch it. However, we get around this by we can then delete it later, and then we can create another buffer if we actually want to modify that. But in actual practice, you generally don't modify it very quickly. Now, if we had something we were modifying constantly, you can do a dynamic draw, or there's a streaming one as well. But I'm lazy, let's just do static draw for now. So one thing that's interesting is we're going to have a bunch of these for each type of attribute, but really they need to be linked together because when you're drawing, we need to know the position, color, and UV and all the different attributes together. We're going to use something called a VAO, which makes this very easy. But we need a function that sort of lets us bring these all together and focus on one and use it. So let's make this here. We'll get a reference to GL. Location is the number that it is. So maybe position is 0 and maybe color is 1 and maybe UV is 2, etc. Okay, so what we're doing here is we're basically saying that, okay, for position, like we're going to put it at 0 and we're going to bind it to array buffer and then which we'll use in a little bit. And then we're going to say for the 0 one, this is the info about it, right? Our elements per vertex. We'll do this one in a second. This is a conversion for the type in which it is. And then these, we can ignore this, but there is some fancy things that you can do with these properties. Whether it's normalized, I almost never use that. But stride and offset are cool if you want to do stuff, but we'll just ignore it for this one. Okay, and then what we're going to do is we're going to create a nice function for converting our types like integer and float into the ones actually on WebGL. And we'll just, to be exhaustive, we'll throw that in case we want to add more types later, just so that we remember to do this. Okay, so now let's talk about our mesh. So our mesh is going to have, we already talked about vertex attributes. We're going to have a couple of those, but we're also going to have indexes, right? So 3D geometry and graphics is made up of dots, which we talked about. And then we need to make triangles out of these dots. And the way that we do that is with indices. So each dot we've already talked about that. The triangles are formed by indices, and this is what they look like. So every 3 numbers, it basically says, okay, make a triangle out of the first dot, the second dot, and then the third dot. Oh, and then make a triangle out of the second dot, the third dot, and the fourth dot. And obviously 0 is the first dot because numbers start at 0 with computers. And so these indices, every single 3 of them is going to be a triangle. There are other schemes for making geometry out of indices that use less indices, but for now, we're just going to do this. This is probably the simplest one and most straightforward. So come in here, let's make a bunch of vertex attributes for each one, right? We'll have 1 per attribute. So if we have position and UV, we'll have 2 of these. And then we're going to have a list of indices, which is numbers that will look something like this. We talked about VAOs earlier. A VAO is a nice object that is on our graphics card that we can just use to say, hey, we've got all these vertex attributes. I don't want to juggle these. I just want you to know about all of them and just use them. We'll show how we do that later. And then just like for each one of the vertex buffers, we also need an index buffer, which is the memory on the graphics card that stores all of these indices. What did I just do? This variable is on the CPU, but then we can buffer it on the graphics card. Go ahead and create a nice constructor that brings in all of our vertex attributes. All right, and then we have a nice function that will buffer both our vertices and our indices on the graphics card. And then we have nice helper functions that do that. For each one, go ahead and just set up a reference for WebGL. Now for each one of our vertex attributes, position, UV, etc., we want to buffer it. So we'll have 1 buffer for each attribute. Okay, so this is where the VAO concept comes in. So basically what we can say is, okay, we've got all these, vertex attributes. I don't want to juggle them all around. So we can create a vertex array, a VAO object, a vertex array object. And then what we can do is we can say, okay, bind it, right? We're going to use this VAO and we're going to attach all these vertex attributes to it. And then later, when we want to do the drawing, we just pass the VAO. We don't have to worry about all these buffers or anything, but you still need to keep these buffered. We're just saying, all these are connected together. For our vertices, it's really similar. So we're going to delete the buffer if it already exists. And then what we're going to do is we're going to create the buffer and we're going to bind it and say, hey, we're using this element array buffer. And then whatever is that element array buffer, we're going to buffer all the indices and static draw like we talked about earlier. We're going to put it in memory that we cannot modify later. And this makes it a lot faster. Now, this actually is somewhat inefficient. If you're familiar with OpenGL or WebGL, you can actually use 16-bit indices to reduce the amount of memory that you're using, as long as you have less than 65,000 of those in memory. We can use 16-bit and it reduces the amount of memory slightly. I'm lazy. For the sake of this video, we'll use 32-bit. Actually, what would be nice is if we just automatically switch between the two and you don't have to actually worry about it from that. But either which way, let's just use 32-bit for now. Okay, and then finally, we're going to do our draw code, get a reference to GL. Instead of having to juggle all of our different vertex attributes, we're just saying, hey, use this VAO. It's actually also easier on the CPU as well. Let's go ahead and actually bind our indices as well so that we can do that. And then this is where we actually draw everything. So draw elements takes in vertices that are indexed by some kind of an index buffer. They don't have to be, but then you're very constrained. And indices are nice because you can reference other points in the geometry and stuff. Anyway, we've got GL triangles basically says that every 3 indices is a triangle. So these 3, next 3, next 3 would be like 3 triangles. And then it needs to know how long the indices are. And then it divides this by 3 and it figures out how many triangles there are. We're saying that the indices are the format of unsigned integer. If you're using 16-bit, we would say unsigned short if we want to save memory. And then this is actually a offset. So if we wanted to start from a different part of the memory, we could, and then we could also modify this. If you want to store like a longer thing and have multiple meshes inside of it and you want to do fancy things. But we're just saying for now that we're going to use all of it in that single mesh. And finally, we'll make a nice function that just says whether the memory is actually buffered yet. Okay, this has been quite bit of code. I take my hat off to you so far. Thank you so much for following with me with this. Couple more steps. We want to do the material. We'll jump straight into texture. Some tutorials, they start you off with a triangle, and that's cool. Maybe I could have done that, but we'll just jump right into it. Before we do that, we need one more utility class, which just stores a single two-dimensional array. Go into Engine and create a new folder called util, and then we'll also create another file called Array2d.ts. This is going to store two-dimensional data of some sort. I always like making a class like this instead of making arrays and arrays inside of arrays. I just like having a class that stores data in a two-dimensional fashion. You can actually store it just with a one-dimensional array. So the data could be laid out like this, but it really, when the user accesses it, they think it looks like this. But if you look at it, 0, 1, 2, right? It could, lay out there. 3, 4, 5, and then 6, 7, 8, right? Anything that's two-dimensional can be made one-dimensional. There's an equation that we use to calculate this, and this is that. So you can pass in y and x and multiply y by width, and then you get wherever it is in here. Start off by the data itself, which is generic, and then storing the width and the height. Create a constructor which stores the width and height, and then some kind of a factory pattern which creates t. This is useful because we can actually not just store numbers, but store other things as well. So we'll store the width and height, and then what we'll do is we'll fill the entire array with that data from our factory. So let's create a nice set function. Takes a piece of data, and then the user can just specify an x and y, or by user, I mean you, the programmer. And then we have this nice algorithm here, which can be used to find where it needs to be stored in the one-dimensional space. Do this as well for your getter. So your getter, instead of taking in a value, it's going to return either t or undefined if there's not a value there. And we'll just return that. And finally, we want to return width and height. We'll just do getters for those. And that'll let us be able to query them later. Okay. Now, with that being said, we have everything in place to create our textures. So textures are images that we'll use to render into the world. Let's go ahead and we'll jump into visual and our texture.ts. So we'll end up importing the following. Let's create a texture class. Images are really great because instead of having tons of geometry, we could actually just have an image, and images have a lot of detail to them. We'll use our nice fancy Array2d class that we just coded, and take a look at this. We can store a two-dimensional array of colors. Like with the shader and the mesh, we're going to have some GPU memory that actually stores the texture on the graphics card. It could potentially not be buffered, so we can set it to null here. There's several different ways in which we can make an image. So one of them is that we might just want to make an image with a given width and height. And what this does is it'll give you an image that has just the color black all filled out with that. Or I guess that's a shade. But anyway, yeah, so we're just basically creating a new array, width and height. It does the heavy lifting, and it fills it with the color black. This is useful if you want to actually modify the pixels later on. Another very useful function sometimes is to just get a single color. So we'll create a nice, we can't create multiple constructors, but what we can do is we can use static. So you can just type texture from color and to say new color, and do like that would give us, for example, a texture that's green. So anyway, go ahead and add this function here, create a new texture of 1 by 1, just 1 pixel, and then sets the color and then returns it. Now, what we really want to do is we want to be able to load images as well. These are useful if we want to do procedural generation or, fancy things. But oftentimes we just want to load an image. So we'll take in a HTML image element. This is an image that's already been loaded in. This code right here, what it does is it actually spawns some kind of an off-screen canvas. It will render the image into that canvas. So the canvas is the width and height of the image. And then the canvas itself, once it's rendered into it, we actually can get the raw pixel data from that by saying get image data. And notice we called canvas get context 2D. We could have done WebGL2 here if we wanted a WebGL context. There's many other kinds of contexts that you can put in here, but 2D is another one that we can use. Come in here and create a two-dimensional loop. We're going to make a new texture with the image width and height. Now note that the texture stores the color information with our color class, so we need to put that in there. Very similar to our fancy function that we had earlier, we're going to do that to get the index inside of these pixels for each thing, and then multiply by 4 because we have RGBA, right? Red, green, blue, and alpha. Come over here, just be kind of careful as you're typing these in. We're going to actually set the texture data at a single pixel, right? So this would be for red, this would be for green, this would be for blue, and then this would be for alpha. And then we're setting it at this X and Y coordinate. And finally, we just want to come in here, we're going to say return texture at the very end, right? Notice there's two curly brackets there. Cool. This is for an image that's already loaded, but as a convenience function, we also want to just add a nice function that adds from a URL. We can also create a really nice convenience function for just loading an image from a URL, so we don't have to do all the fancy things with HTML image and all that. Come in and do that. Now, we're going to start with an empty texture because the image is going to be loaded in, and we want to be able to use this texture while it's being loaded. In fact, modern graphics engines do that in order to decrease the load times and things like that. I think it's a nice feature. Let's do that. Let's create a new texture and then go ahead and create a new image and get the, as soon as you do this, it's actually going to start loading the image. And then what we're going to do is we're going to do add event listener. We're going to listen for load and then comma space. Let's add a function right inside of here for when we're done. Inside of here, we're going to piggyback off of our loaded texture and we're going to set the texture to this. And then these are two functions we're going to add later actually. So we're going to add an isBuffered and then a buffer similar to what we did with the mesh and the shader. Okay, and then after this image load, right here, what we're going to do is we're also going to add some code for handling an error. We need to know if the texture failed to load, and so it doesn't fail silently. So let's go ahead and we'll handle that properly. Now, even if it failed to load, we still actually have a texture because we created one earlier here. So go ahead and just return the texture regardless. Now, WebGL actually takes in a uint8 array for a regular color texture. There is other formats you can use if you want to do high HDR rendering, high dynamic range, or if you want to do other fancy things, or if you have other kinds of data. But for standard RGB, works everywhere. You have 8 bits for each one of those. Let's make a helper function for that. So we're going to take the data that's in the current texture and then convert it to a uint8 array. We're going to get the width and height of the data. Again, we have these nice functions that do that. And then the size in bytes is going to be the width and height times 4, right, for RGBA. Okay, and then we're going to create a two-dimensional array here that's going to loop through first the Y and then the X. We're going to get the actual color at that location. And then again, we're using our fancy function here. You might notice that actually this is quite common, that we'd actually have to write this all the time a lot more if we didn't have our Array2d function that we did earlier. So like I mentioned earlier, like even in WebGL, even though we have two-dimensional textures, we still pass in the data via a one-dimensional way. So kind of being familiar with this is really good. You'll see this a lot. Now remember that our colors are from 0 to 1 for each one, where 1 is like 100% and 0 is 0% red or green or blue. So we need to convert them into 255 for bytes. So we'll do that with, we'll multiply each of these by 255 and then we will round it here, right? So that's not some decimal. And then we'll set that to red, green, blue, and then alpha. And then finally, let's return the buffer here. Okay, we created a buffer function earlier, which actually sends to the graphics card. So just like our shader and just like our mesh, we also have a function which sends the texture data to the graphics card. You kind of know the routine right now. Let's get a handle to GL. And just like we were talking about with our mesh, we can also delete the texture if there is a texture now. So we'll check to see if there is one, and then we'll call delete. I hope you might be seeing a pattern here. We're going to create a texture instead of a buffer. And then just like with our buffers, we're going to bind it, but instead of array buffer, we're going to bind it to texture2d. Okay, text image 2D takes a lot of things in. The texture, target, texture target, target, which we set earlier. Level, we're only buffering one level, so it doesn't matter. RGBA, which is what internal format. There is also this format, which is a storage format. The width and height, border, I never use this. And then what the unsigned byte, which is what format is each number in, which we did earlier. We converted them into byte. And then the uint8 array, which is the actual data itself. We're calling our nice function here, so we don't have to figure it out. Now, WebGL can actually generate mipmaps for us, which is which are a bunch of different versions of the texture, but less and less detail. It's actually very useful for if the texture is very far away. Otherwise, it can look very grainy, but yeah, this is a nice function that'll just do it for us. And then we're going to set, we're going to keep track of it with our GL texture handle here. Cool. We have another function which just says, is this texture buffered yet? Similar to the ones that we did earlier. When we actually go to draw the texture, we say this bind function, which says, I want to use this texture now on the graphics card. Now we can actually have different textures that are bound, and sometimes you can mix the textures and do cool things. We'll take that in if we want to use multiple textures in a single draw. We'll activate, so there's actually a bunch of these. If you do GL texture, watch this, there's like tons of these texture. Notice there's like 0, and you can go all the way. How far does this go? Yeah, I think it goes to like 32. Anyway, but you don't have to remember all those codes. You can just do texture 0 and then add to it. That's the easiest way to do this. And then we bind the texture saying we want to use it. And then finally, we're going to clean up our, have a function that cleans up our texture, which just calls delete texture and sets that. Now that we've done the texture, we have everything that we need to start with our material. So let's go ahead and jump into material.ts. Give yourself a pat on the back if you've made it this far, by the way. I think that this is the last file that we have part of our graphics in. A material tells the graphics card how to draw everything. It brings the shader, which is the actual code of how it draws it. It brings in things like textures, and it also brings in like uniforms, which are variables for controlling how something is drawn. An example of a uniform is a light source, right? Which may apply to the entire geometry. So yeah, what we'll do is we'll import the following, and then let's come in here and we'll create a class for this material. We did the shader earlier. That's the code that is actually executed to draw the object to the scene. And then, like I mentioned, uniforms are variables for the entire mesh itself. Let's make a material by taking in a single shader and then any uniforms that we want to add to it. And then we have a function similar to the other ones, the bind function, which basically just says, hey, start using this material to draw things. And so it tells the shader, this is the current shader that we want to use. And then it also tells each uniform to bind as well. Now these are errored out, and that's okay. We're going to create a uniform class here in a second. A uniform, like I said, is a single variable that describes how to draw something, like a light, or like our matrices that we created earlier for how to move or orient a model so that it fits on the screen. They represent a variable that applies to all of the either vertices or all of the pixels on the screen during that one draw call. Every single uniform has a name. This is the actual variable name that will be in the shader program that we do. And then this is the actual location inside of the code of where that uniform is located. We'll create a nice constructor that takes in the name. The location we'll find, and we'll compute that in a second. When we set up the uniform, we want to call this prepare, and this finds the location. We'll code this in a second. The isReady function is just very similar. It sees whether the uniform has a location. We need that location so that it knows where to actually put the memory. And finally, we're going to bind, which basically says, okay, start using this uniform for drawing. Now this right here, this get uniform location, let's actually go back just real quick to our shader class and add that. Very, very quick. Let's go to shader.ts. I think what we'll do is go right before the bind class. Not bind class, bind method. Let's do the following. So again, a uniform is a variable that's in the script. We'll create this entire function right here. And then what we'll do is we'll get a handle to GL. We're going to call, GL has a uniform location that it has. And then what we'll do is if we didn't find it in that script, then we want to throw an error, right? Because you're looking for a variable that doesn't exist. This is very helpful to you later on if you forget to add it to your script or something. And then we'll return it to we'll return the location. Okay, let's come up. One other one real quick while we're here is, and I apologize for this, let's add one more thing, and that's the attribute location. Attributes again are the, I forgot to do this, I apologize. Attributes are the geometry, right? We said position and colors and UV and things of the mesh. You can also do the same thing as well. I think this is a nice function, very similar. We're just going to get GL, call get attribute location, and then if the location is -1, that means we didn't find it in this case, and then we'll throw a new error. Okay, very good. So let's now jump back into material.ts. And now this shouldn't be errored out. Now with uniforms, like I said, they're variables, and we can actually have different types of variables. If we want to be really exhaustive, we would make a massive list of them. But let's just add a few useful ones here so that we can start drawing. One kind of variable that we can have is our texture. Textures will actually have a sampler on the graphics card where it has information about how that texture should actually be drawn into the mesh. Let's actually store a reference to the texture that we want to draw. And then we get the name of the variable that we'll have on the shader, and then the actual reference to the texture, calling super, which is the constructor for the uniform, and then we pass in the texture. And then finally, we must implement a bind function, which basically says, okay, how do I know to start using this variable? And so we'll do that. We'll bind the texture, and then we'll also bind the sampler, which is the variable in the actual shader itself. Another kind of variable that we'll need is a matrix, primarily for moving positions around into where they need to be. Let's hold a reference to this matrix. And then with this one, we don't need to do any binding of that. We just directly do bind on the script itself by calling this. Two more. Let's hold a single number, so uniform float. This will be useful later when we have an ambient light, which just kind of lights everything in the scene. Come over here and store a single variable, and then do our constructor as we did earlier. And then go ahead and bind it by doing that. We're calling this instead. Last one that we're going to do for this video. There's others, but this is these you'll probably use most of the time. This one holds 3 numbers. Go ahead and store the following. We probably could have used vec3, but that's okay. Go ahead and do this, and then go ahead and take in each one of these numbers like so. And then we're going to go ahead and call bind like this. Okay, so now the graphics code largely is basically done. Let's do the shaders, and then we'll get into Billboard. Come in here and go into Engine and create a new folder called Assets. Do these, close these, and let's go ahead and create asset map.ts. We'll come back to this one. This is a mapping for our different common shaders that we'll have. Now again, each shader is going to have a vertex and a fragment. I know that this is a lot of information, but it's going to have a vertex and a fragment stage. So we'll create one for the fragment. Let's go ahead and create texture fragment.glsl. Go ahead and also make a new file, texture texture vertex.glsl as well. Go ahead and type the following. So in the texture vertex, what we have is we have 2 vertex attributes, right? Remember those lists of positions that we had and UVs. So we have position, and then we also have UV here. We're taking in a uniform, which is the camera matrix. This is a variable that is applied to all of the vertices in the mesh, all the dots, to move them all to where they need to be onto the screen. And then we're going to output only the UV. GL position is a special output variable as well that's baked into vertex shaders that we'll also set. This is the code that is run on every single dot in the geometry, right? Every single vertex. So we're going to ultimately get a GL position, and take a look at this. We're taking the camera matrix that we have, and all we do is we multiply it by the position. Now, the position actually needs to be a 4-dimensional vector. So we're taking the X, Y, and Z position, and then we're applying 1.0 to that. You'll see this a lot because this is a 4-dimensional matrix, which actually holds all of the rotation and position and scale and the transformation of the camera and the transformation of the projection all into this one matrix, all in one operation. That's why using matrices is so beneficial, because we could do like 100 different operations all in this one matrix. And then what we'll also do is we'll pass the UV through to the next stage. Now, one thing that happens after this point is you have the rasterization stage. So this, all the dots will then turn into pixels, and then we operate on those pixels. But what you also have is you have an interpolation, which happens. So for each pixel, it's going to have a UV coordinate of some sort that's sort of in between the triangles. And then the pixel shader, the fragment shader later will be able to use that. So now that we've got the position on the UV, let's go ahead and go into the fragment. Now in the fragment shader, what we're going to do is we're going to set the precision of floats to high. You can actually modify these for performance, but sometimes you want high precision, which makes things a lot. There's a lot more values in between the values. And especially for things like UV. Otherwise, you'll have these like stair steps and kind of weird effects if it's low precision. But sometimes you can do low precision for more performance. We're taking in the UV coordinate. Remember that. So we just converted a triangle into a bunch of different pixels, and so for each pixel, there's going to be a nice UV coordinate that's sort of interpolated, right? The values in between those two different things for that particular pixel. We have a uniform here, which is our texture, that sampler 2D, which kind of tells us how and what texture that we're going to sample from. And then we have our the frag color. The fragment color is going to be what actually outputs to the screen. So what we're going to do is we're going to set our fragment color to the value of just doing texture. Now, texture is a function which samples a given texture at a specific location. So this is our coordinate of where we are in the texture, and there's the texture itself. Now, this right here, basically what we're saying is if the alpha is 60% or less, we want to just throw the pixel away. We want to discard it. You can adjust this if you want, but this is an effect because we'll be working with some billboards and things, and the lower that this value is, the more that you'll start seeing the transparent part. So I just put it to 0.6 for now, but you can modify it. Okay, this is now our shader. So let's actually go to our billboard code. Let's go into components and let's go to billboard.ts. So billboard is an image that kind of always faces the camera. So it will rotate towards the camera. And it's been used in games to put an image into a 3D world without an actual geometry. It's just sort of like a rectangle of an image, and then it just like always faces the player. Okay, so now that we've done that, let's go into assetmap.ts. Really quickly, what we're going to do is we're going to import these and we're going to export them. This will make it really easy later on so that we can just say, oh, I want the texture fragment GLSL code, or I want this code. We don't actually have to worry about loading it. It's just going to be baked in and we can just reference it later. The nice thing about the asset map is that we can then just type this and we just get the source code for it. We don't have to worry about, getting a specific location of this later or anything. This is a nice thing that Vite supplies. Now you might notice that these are erroring out. We need to really quickly tell TypeScript about GLSL files because it normally doesn't, it it kind of doesn't know. It's like, what is this? Let's go ahead and jump into your engine and right click and create a new file called GLSL.d.ts. And this really short file basically just says if we ever have a GLSL file, it's just a string, just load it as a string and set the content to string. We can do fancy things with this, but we're not going to. One last thing is that Vite with this, before we get into Billboard, is that Vite itself is going to also want to hot reload these files. Go into game and go ahead and create a new file, and we'll call it Vite config.js, and we'll hit enter. Add the following. So what we're saying here, Vite is our library that we use for hot reloading. As we change the code, it actually reloads. And then it also takes all the code and it will package it and put it on your website later, that you can use to put on a website later or that sort of thing. We're saying that we want to host a dev server if we do npm run dev. And then we're just creating a plugin that can also load the GLSL. We'll just call it this. And basically what we're saying is just load it, export defaults, and we'll go from there. Basically, this code will just load that file and allow us to do it in Vite. Okay, let's come in here. And now that we've done all this, let's finally go into billboard.ts. Don't feel like you have to write all of this, but as you're typing, you can import these, right? So like, let's say that you type export class billboard, extends, and then as you're typing component, see how it like comes up here, hit enter. So these will come in and autofill as you type and do things. But just if you hit any issues, this is the full list of imports. So this is a class basically that has a single picture that just always faces the camera. And they're very efficient. And I think it's easier just to have billboards at the very beginning, because then you can create an image and it's just really fast to add things to your game. You can replace it with models later, and we'll probably do models at some point. But yeah, let's start with this. A billboard is going to take in a single texture of some sort. And then it's also going to take in a material, which is how we're going to draw. And then it's going to have a location. The location is going to be on, this is a component, so it's going to be on the entity, but we'll go from there. And then an MVP matrix, which stands for Model View Projection Matrix, which is our final matrix that we get when we're drawing. When we make these billboards, we want to make it really easy. Let's just go ahead and take in a texture. And then this is a component. So we're going to do the onStart function. And then we're going to expect a location to already be on this thing. But if the location is not there, then we'll add it lazily. Go ahead and add yourself to the location, and then we'll register ourselves with this. Now, the reason this is erroring out is we just need to implement those functions. We'll do that in a second. And then when we're done, we're going to break this down. We want to unregister so it doesn't draw anymore. Now, every single billboard is going to have a mesh that's going to share. There's no reason why we need to make a new mesh for every single one. And it's also going to share a shader as well. So come down here to the very, very bottom. Okay, so and then this is where we're going to make our rectangle that actually has an image on it. So this is going to be the bottom left corner. This is going to be the bottom right corner. This is going to be the top right corner. And then this is going to be the top left corner. And then these are our UV coordinates, which is how it's actually mapped onto a texture. And then these are our indices. So we have two triangles, right? Two triangles can make up a rectangle. So we have our first one, which is 0, 1, and 2. And then we have 0, 2, and 3, which is 0, 2, and 3, which will make up our two triangles that way. The other thing is that every single billboard can just share the same shader. We don't need to load the shader multiple times for every single tree. That would be ridiculous. So we're going to make a new shader, just one, taking in our and we have two stages, right? So first is our vertex stuff where we take all the dots and we move them. And then the second one is our fragment, where after those dots, we get pixels, and then we actually render the pixels to the screen. Okay, with this being said, let's go ahead and jump back into our billboard class. Let's get the very bottom of it, and we'll go from there. Start typing setup, and we'll hit enter. We're going to lazy load our mesh. So yeah, we defined the mesh, but we didn't actually put it on the graphics card. So for the very first billboard that you make, it will put that mesh on the graphics card. For any ones after, it won't need to. We're also going to lazy buffer our texture as well. So if the buffer that we're supplied isn't buffered yet, sorry, if the texture that we're supplied is not buffered yet, then we're going to buffer it. And then what we're going to do is we're going to take our material and we're going to set the camera and then the texture. Now we need to add the camera to visual. We'll do that in a second. We don't really need to break anything down, so we'll just do that. And then we'll start typing our draw function and it will fill it out for us. We need to add the camera to the visual, but yeah, either which way, we'll rotate towards the camera by doing the following. So we get the camera and then we get where we are, and then yaw is rotating left and right. So we need to rotate this to the right. And what we can do is we can do the camera rotation, the camera and the position X and the Z. This gets an angle that we need to rotate by. And then we just do a quaternion to rotate it. Okay, so then we're actually going to draw. So what we're going to do is we're going to get our location and refresh it. When we refresh it, we take the position, rotation, and scale, and we get a matrix from that. We then use that matrix and we combine it with the camera matrix in order to get an MVP matrix. This is one matrix that will position, rotate, scale, move it towards where it needs to be on the screen, and then also project it. All 5 of those things, all in one matrix. That's why matrices are so powerful, is that we just do one operation and it's like it has all those 5 baked in. We will then add this matrix as a uniform, right? Uniforms are a variable that is applied to the entire mesh. So all of the dots, all the vertices of the geometry will then be multiplied by this matrix to position it where it needs to be. We will then tell the graphics card that we want to use this material when drawing, and then we will actually draw the mesh. Okay, and then let's go ahead and let's go back into the visual, and then let's go to visual.ts. Let's add that camera real quick. Come up here to the top and find where it says drawables, and then we'll go ahead and we'll add our camera there. And what I can do actually is I can just say camera and then it'll add the import. Okay, so that did that and it just added the camera there. Now that we've done this, find your constructor, and what we want to do is we want to go to the very end of it, find where we just do that depth function there. And then we want to add the following code. So I'm just going to type in perspective camera. It'll also add an import up at the top for that. So just make sure if you are hitting issues, just make sure that that import is up here as you're doing that. Okay, and then just go back to billboard.ts and then all the errors should be gone. So that, yeah, there we go. Cool. Finally, we can actually test this out. Let's go ahead and find the game and let's go to main.ts inside of game. What we want to do is we want to upload some kind of an image for our billboard. In the link in the description below, I have a link to some assets of trees and a watermelon and things that you can download. That will be the game assets that we do later. Feel free to download that as well or find an image that you want. I'm going to come over here. I'm going to bring this watermelon over to assets. And then, yeah, we have a nice watermelon image. Okay, let's go ahead and go back into game and then main.ts. Up at the top, we could make an asset thing, but we won't do that for now. Let's just do import melon from type assets, and then we'll do melon.png. Okay, and then this is probably going to error because we need to add a TypeScript thing for it. So we'll do that in a sec. This is going to error because we need to add a TypeScript thing for it. In game, add one more file. Let's do assets.t.ts. And then this is going to tell it to load PNGs. So I have like anything that is a PNG, similar to what we did earlier. We have a URL with it. Let's go ahead game and then main.ts. So now we're loading our melon. We're going to get a texture from that. So we'll say texture. And if it's not helping you out, what you can do is open up your terminal. You can stop it if you want, and then come in here and do npm install and hit enter. And then it may actually start. If it still doesn't help you out, and sometimes this is the case, come up here and go to import and just do it directly. So it's import texture from, and then we're going to do engine/. This is visual and then texture. And then VS Code will know what's going on. So as you're typing out, yep, now it knows. And we're going to do from URL, and we can just pass in this million directly. This is what's so nice about these asset, like just importing the asset like this. While we're at it, let's go ahead and import our location. And let's also import Billboard. Now that we did this, VS Code kind of gets with the program. Sometimes it doesn't still. So we'll do component or engine components and Billboard. If it's also not importing, just make sure you don't have to go here, but just make sure that on your classes you did export if you're not seeing it or you're getting errors. So now let's come in here and let's say engine world make entity. And let's make, so an entity again has several components. So let's give it a location. This location, we are going to fill in a position, but these other ones we'll leave as default. Let's come in here, we'll do 0 for X, we don't want it left or right. Let's do 0 and let's do 10. Let's do new billboard, and then we're going to do texture, and we're going to do that. So we're putting in our million texture. If everything worked, and it didn't, we have an error. Okay, so let's take a look and see. So if you have an error, because we changed Vite around a lot, you can do Control C, and then you can also just do npm run dev again and hit enter. And we have nothing. There's nothing drawing, and it doesn't work. This is very common, and I actually forgot something, so let's add something. But I wanted you to see this because, even somebody like me that I wrote all the code previously, you can actually hit issues like this. The reason why this is failing after some research is because I forgot to add the camera update to the visual. That's a very small thing. Let's go to visual.ts. And then let's come down here to go find where it says depth function and where we actually create the camera. We need to come in here and we need to say this register, and we need to actually register the camera itself. And that will draw everything on the screen. And now we've got our melon. But you might notice that the watermelon looks very, very strange. And that's because if you recall from a long time ago when we just had that tiny little box, the tiny little box for the canvas that was on the screen here, we never told the canvas how large it is. And so it's still using that really, really small resolution. So you have barely any pixels to work with. Let's fix that. Come in here. Let's create a function called resize. So we'll say private on resize. We don't want to fix it just now. We actually want to fix it also if the canvas resizes. Let me move my head. Okay, so we'll get our GL. We need to figure out how big the canvas actually is. So we'll set the canvas attribute, the width and height, to it's the window's inner width and inner height. If we are wanting the canvas to not be the size of the screen, we need to change these later. WebGL has no idea about how big it actually is until we do the this thing. And let's actually come in here and call it. So inside of right where we registered the camera, let's do this dot on resize, just to call this function. And watch this. Now the pixels actually get a little bit better for this, but we're not done yet. We still need to update the camera. So right now what's happening is actually the projection matrix, it doesn't know how big the width and height of the screen are. And so we need to tell the camera that. Let's tell the camera how big it is, and boom, it instantly is now fixing that, because we now know, the camera now knows how to project it. And finally, let's go ahead and call actually refreshing the projection, and that will more properly do it as well anytime it changes. Now, what we'll do is we're still not, if we do this, watch this. Yeah, so if we change the size, it's still not refreshing. So right after this on resize that we call, we're gonna come in here, we're gonna window, add event listener, resize. Let's make a little arrow function here, and let's come in and we'll call this on resize, and we'll do that. Yeah, and then what we'll do is now we've got, if we resize it, it will now stay. And there we go. We have a billboard. And now, if you're not seeing a watermelon at this point, we wrote tons and tons of code, and you know, there might be something that might have been missed or whichever. Don't feel bad, right? I wanted you to see that the first time that I did it, I forgot about this code to even add it. This can happen to all of us. I want to remind you that all of the code is in the description below. So don't feel bad if you want to just take, you know, your texture class and paste the code that's in the description, you know, over it or whichever. Believe me, this can be very difficult, especially with graphics programming, because it could be the camera has an issue. It could be that the camera is just not facing the object. It could be that the object itself is placed wrong. All sorts of different things. With main TS, one thing you could instantly do is you could play around with this location. Like maybe you need to do negative. Watch this. Now I can't see it anymore because it's behind me, right? And so, you know, if I do 0, now it's in the middle here. That's the thing, is there's so many things that could actually go wrong, and it's very difficult to test with graphics programming. I would also recommend at this point, I know, you know, say what you want about AI or that sort of thing, but in 2026, AI is incredibly good at debugging or helping you debug graphics code. So you can either look at the code that's in the description below. If you get stuck, please don't spend an enormous amount of time on it. We've covered the concepts and it's so easy to miss something. But once you're at this point where it's actually drawing to the screen like this, it gets easier from here because you know that the camera is working and you know that all the other systems are working. It's loading the texture into memory and stuff. So yeah, this is really good. So now what we're going to do, now that we've got these billboards, is we'll create tons of them on the screen, right? Because we're going to need it to create tons of trees. So let's come in here. I'm going to go and I'm going to do this. And then let's come in here. We're going to add one more thing to our util class, and that, or sorry, util folder, and that would be random.ts. And we're going to add a really, really simple random number generator that just gives us a random number between a minimum and a maximum. So this right here is a number between 0 and 1. We multiply it by the max and min, like the range, and then we just add the minimum back to it. Okay, so now that we've done this, let's go back to main. And now we're going to have a single texture for every single one. But let's come in here, we'll create a for loop. So we'll say for let I equal 40. Yeah, there we go. We've got a for loop that loops through 40 different things. Okay, and then we're going to randomize the X and the Y coordinate. This can actually, don't do that. Let's do 10 for this. Random, we need to import, and if it's fighting you, just go ahead and do it manually. Go ahead and do random from engine, util, and then it should know it, and it should be good to go. Oh, because I misspelled it. Look at that. Okay. Okay, there we go. Then after that, take this code right here. Let's just paste it into here. And we'll do that. And then what we'll do is we'll do location. And then let's go ahead and see what's going on. And now we have tons of watermelon all over the place. Very good. So now that our billboards are working well, 2 more things I want to do in this video. I want to do a fly through camera, and then I also want to do terrain as well, and then we'll be done. I know this is quite a long video, but this will give us a really great foundation for our game later. Let's go into fly camera. So engine, components, and fly camera.ts. Let's import the following. So our fly camera is going to be able to move the camera around via the controls. Now, we actually need some way to take user input in. So let's do that really, really fast. Let's go to engine, create a new folder called input. And then inside of there, we'll create a new folder called input.ts and hit enter. Input is a very basic class that what it does is we'll take down, or sorry, user input. It keeps a set of different keys that are currently pressed down. And every time that a key is pressed down, it adds it to that set. And then every time a key is up, it deletes it from it. And then we have this nice function that we can call at any time to see whether a key is down or not. Let's add this to our engine. So let's come over here, engine. I know there's a bunch of folders. Engine main.ts, create a user input field. And then right here, let's come in here, engine input equals new user input. Okay, and then what we'll do is we'll jump back into our flyCamera.ts. So engine components flyCamera.ts. Let's set a basic movement speed. I'm lazy. I'm just dividing this by 60, assuming it's a 60 hertz monitor. If your monitor's faster, it might be faster. We can deal with that in another video. And then we're also going to keep track of the movement so that we're not making it every frame. Tell the engine that we are an updatable thing. The only reason this is airing out, we just need to implement it. Let's come in here, we'll implement on update. Yeah, now everything goes away. So now this is where we're going to modify the input. So, and you can modify these keys if you want. You can do, I think it's like arrow left if you want. But I'm just going to use WASD and then G and H to move, to fly up and down. Each one of these has a addition, so it's adding the two. That means like if you press A and D at the same time, it'll just do nothing, which I like doing that. Some games it like does one or the other and I don't like it. I use scale, but basically scale is just like multiplying some things. So we're currently multiplying the movement by the movement speed to determine how our next position in the frame. Like we did earlier with the camera, we are moving based on the rotation of the camera, like where the camera is actually facing. We're now taking how much we're going to move and we're going to rotate it by that rotation. So if the camera is facing west and you try to go forward, you're going to go west. You're not going to go north. And then this is just a unit of movement, but we're actually going to add it so that we get the future position of that. And it's going to end up, this is the destination here. We're adding these two things and it's going into this memory. I probably could improve this. I don't want to be creating a quaternion every frame, but it's fine for the sake of this video. We can clean it up later. Let's go ahead and we'll get a rotation here of the camera. And then what we'll do is, so Euler angles are your yaw, which is left and right, pitch, which is like rotating up and down, and then roll, which is like going like this and that. We want to, when we do Q, we want to go to the left, yaw to the left. And if we do E, we want to yaw to the right. So we get an Euler angle here, and then we multiply the quaternion. Quaternions are awesome because you can do this kind of thing and they don't lock up or anything. Okay, so let's actually use it. So let's come into game main.ts. Go ahead and import your fly camera that you just made, and then go ahead and add the fly camera to your world. Now, if everything worked out correctly, we should be able to click, make sure you click on it, and then go ahead and move it around. And it works. And we're able to fly through our massive like thing of watermelon, right? And we're able to navigate around and stuff. So we're in like 3D, we're in full 3D. And the other thing is the billboards are facing us. So we're able to do that and we're able to move around and stuff. So now welcome to 3D, right? Okay, the last thing I want to do for this video, I want to do two other things. I know that this video is massively long, but I promised you that we would do a terrain to actually do the landscape, and then we would do trees. So let's do that. Let's come over here and let's go to engine components and then terrain.ts. Okay, so the last thing that I want to do for this video, I know it's super long, but I want to actually do a terrain in this video as well. So we'll do, let's do the shaders for that. Go ahead and go into assets and let's create two shaders. Let's do color lit dot fragment dot GLSL. And we'll do color lit vertex.glsl. Okay, so for this, the terrain, we're not going to put textures on it, at least for this video. We'll just do regular colors, which I think is a little bit better to control and things. If we want to do textured terrain, we can do that in another video. But yeah, so let's, our terrain is going to have the following vertex attributes. So all of the mesh, all the dots in the terrain are going to have a position. They're going to have a normal, which is basically a vector that points up from wherever it is, and it tells the lighting engine where to light it. We're going to actually do that lighting in this these shaders. and then the color that we want to use. We have two uniforms. We have the camera matrix, which positions all of the geometry of the terrain into where it needs to be on the screen. And then we have a light direction, which is the direction of the sun or some kind of a global light hitting in some direction. We have the color. So output from this vertex shader. Remember, this program takes all of the dots and then outputs. So we're going to have a color and we're going to have a normal. And then in addition, we're going to have a position. So the position, very similar to the other shader, we multiply it by the camera. This has the position, rotation, scale, and the view matrix and projection matrix all in one. Multiply it by this, and then we want to pass through the color and the normal. Let's come in and we'll go to color lit fragment.glsl. We want to take the color and the normal from the previous stage that we had. So this is now for each pixel on the screen. We have two other uniforms that we're going to have. So we have the direction of the light in which it's coming at. This is high precision, just for more accuracy. And then we have the ambient light, and this can be low precision because it doesn't matter. It's going to be a color. Then what we'll do is we want to get the diffuse light. So light coming from a direction, the algorithm is diffuse light, meaning that if a surface is facing directly against it, it's going to be strongly lit. And if the surface is indirect, then it's not going to be, right? If you look at my face, for example, right, the light is coming from here because there's this window over here, and then, but it's not here. So you can see that this part of my face is actually a lot darker, right? That's diffused light. And it gradually, right, as you go more and more to this side, it's more lit, and you go to this side, it's less lit. We're going to do that. So this is diffuse lighting. We're going to take the normal of our geometry, right? Which is, where each part of the geometry. And then we're going to take where the light is, and we're going to get a dot product. The max is just to verify that we don't go over. So yeah, then what over this value. And then what we're going to do is we're going to get an intensity, which is how intense the light is, a value between 1 and 0. So right here, it would be very high intensity because it's light. And then right here on my head, it would be a lot less because it's not directly hitting the light. So we take this diffuse, right, that we calculated. The ambient light is just a global increase the light by everything. And then what we want to do is we want to do that, which is just whatever's remaining from the ambient, we want to multiply it by the diffuse. And this ensures that it doesn't go beyond 1 and do that. Okay, and then we take the fragment color and we output that. We multiply the color that we have by the intensity. Multiplication always darkens things unless you go above 1. So, generally speaking, this intensity is going to be between 0 and 1. So it's going to take the full color that it could have been, and it's going to darken it however it is. So this is not as dark, and then this is multiplied by a lot lower number on my head. And then we go from there. So now let's go back. Now that we have the shader, let's go into asset map, and then we'll come in and we'll import our shader programs that we just did. And then we'll come in and we'll do these right here, just so we can import them easier in our program. Come in here, so engine, components, and then we're going to go to terrain.ts and just type all this out. No, I'm just kidding. As you're typing things, these will come up, but these are all the imports. If you hit an issue with any of them, just come back to this and just make sure that they're all like this. So what I mean by that is as you're typing things out, like class terrain, extends, and then components. See how components up here? I'm hitting enter, and there we go. Implements, and then drawable. And then, so as you're doing these will pop up, and it'll add them here. So in computer graphics, a terrain is a landscape of some sort. Generally speaking, how you represent it is it's a grid, and then that grid has a bunch of heights to it, and then it will create a rectangle for each one as it goes. We're going to store all the height maps. So we have our nice Array2d class that we can use. And then we have how big each cell is in size. So if we do 4, then the terrain will become 4 times as large. We have the geometry and the how we draw the terrain, the material, if they're loaded. And then I want to store later all the normals with just how we compute this. So this will actually optimize it later. Go ahead and initialize all this. Now this is a component, so we want to call super. But yeah, we'll initialize the height map with the width and height of that. We're going to set everything to just 1. I guess this could actually be 0, but that's fine. And then we'll set the normal map. Everything will be facing up. So this is X, Y, and Z. So everything is going to be facing up initially. The engine implements drawable. So what we'll do is we'll register it and unregister it with the visual engine. And then let's come in here. We'll type setup. It's not setup. Now, just like the billboard, the terrain actually could share a shader with other terrains. So going down to the way bottom here, create a terrain shader. So this is going to be shared amongst all terrains that you create. If you create multiple, you might just have one, but yeah. So anyway, the shader source, the vertex stage, and then the fragment stage will go here. Go back up to setup, and we're kind of coming here. We're going to add, if the shader has already been set up, or not, sorry, if it has not been set up, then go ahead and set it up. And then what we'll do is we will create a material, and this material will have the matrix, the light direction, which direction is it coming from? And then it will have the ambient. So this direction goes 1 to the left, and then 2 to up, and then, yeah. This thing though here, this light direction, will be normalized. So this is a distance of, it's probably like 2 point something. It'll be normalized, so it'll come down to just 1. And then we'll have an ambient light here. Come in here right after the second to last one, and we're just going to add a breakdown. We don't need to do anything at this point. And then let's go ahead and we'll do our draw call, or draw code. So we're going, just like we did, we're going to take our matrix, which positions this on the screen somewhere. We won't do the location for now, but maybe we will in the future, especially if we have like multiple terrains, like we have chunks or something. If we do that, tell the material that we're going to use it when drawing, and then actually draw the mesh. Now, this is the last part of this, and this part can be a little bit tricky for actually creating the geometry itself of the terrain. But yeah, just make sure that as you're typing everything in, just kind of be careful. Again, if you have any issues or run into anything, the code is in the description below if you want to copy these next functions. We're going to make a nice function that gets the normal at a certain location. The normal is the vector which points away from it. So like on my head, it would point away here, and it would go, right, it would be pointing away from something. And it's used for calculating the light. We want to calculate the normal at a certain position in the terrain. So we'll get the height at where it is. There's a couple ways we can actually do this, but okay, so what we're going to do is we're going to average all the different spots. This can be tricky because we also need to get the normal at like parts of the edge. And so getting the right, we might be stepping off of the terrain. So we need to check for each one of them to make sure that we're not off of the edge. And if we're not, then we'll get the value. Otherwise, we'll just default to where it is. And then what we're going to do is we're going to bring all these values together, and then we're going to call normalize to make it a distance of 1, and then we're going to return it. This is sort of the last stretch here on this function, and then we'll get a really cool terrain rendering. So the terrain may not have a mesh yet, and if it doesn't, then we want to create one. Each one of these, remember for the terrain, we want to store the position, the color, and the normal for every single dot in the terrain. And every single cell of the terrain is going to have 4 of those dots, 4 of those matrices. So what we're going to do is we're going to multiply 3 by 4, right? The number of ones that we have per cell. And then we want to get it for the width and height minus 1, right? Because when we get to the edge, we're not going to add anything after that. What we're going to do for each vertex attribute is we're going to say 3, right? Because there's X, Y, Z. Normal also has XYZ, and then the color has RGB. So there's 3 for those. We're going to fill everything with 0, but we're going to pre-allocate it and go from there. The number of indices that we need, so we need 6 because if you recall, 3 is used to make one triangle. We need 2 triangles to make a rectangle. And so we need 6 indices to make 2 triangles. And then for each one of them, we multiply it by the number of cells that we're going to end up having. And then we're going to just fill everything with 0. So really in this, we're just setting up the data and pre-allocating it. Let's now get each one of our vertex attributes and then also a handle to the indices. And we're going to make a nice function too that's going to go through each vertex and then set it up, and go through each index and set it up. So we're going to keep track of where we are for each cell. Now, this function can actually be quite complicated. So what we're going to do is we're going to make a really nice helper function that does this for us. So this takes in an array of and at some offset and sets X, Y, and Z. It's going to be really nice later on. And do this as well. I know that it's kind of like, why are we doing this? But also add this one as well. This is going to make it a lot easier later on to convert the normals. And then what we'll do is we'll just set everything to green. There are some cool things later, like if the train gets really high, then we can set it to snow or something. But for now, let's just set everything to green. Okay, and then now train is 2-dimensional, right? Okay, now we're actually going to set up each one of our cells in the train. So we have our 2-dimensional array that's going to go through each one of the cells. And because for each cell in the terrain, or each tile in the terrain, we're going to have 4 dots to make up a rectangle. We're going to have 2 triangles for each one of them. Let's go ahead and set the normals at each position. Now, I want to preface something. This might seem like a waste to be doing these +0, but there is a method to my madness. So this is x0, y0. This is x1, y1. This is x0, y1. And this is x1, y1. So this right here is the top left corner. Or sorry. Yeah, no, this is the top left corner. This is the top right corner. This is the bottom left corner. And this is the bottom right corner. And that's going to be the pattern for each one of these. Let's do the top left corner for positions. So we have these nice functions which do that. Let's talk about this. We're going to set the positions data at this particular location, which we're going to increment this. We want to get, again, the x plus 0 will make sense here in a second. And then, yeah, we multiply it by the cell size. This will make the terrain even bigger if you set the cell size. So it's the size of how big a tile is in the terrain. And then the height at that particular location, we want to get it. Okay, this is the top right corner. So very similar. We're just copying this, but we're going to set x to 1 and x to 1. And then we're going to set vertex offset +3. Okay, now we need to do the bottom left corner. So vertex offset is now 6. We're having x0 and y1 and x0 and y1. Okay, and then finally, we want to set the positions for the bottom right corner. So we want to do vertex offset equals 9, or sorry, +9. And then we want to do x1, y1, x1, y1. We got the normals earlier. Let's actually set them. See the pattern here? So I can move my head. So vertex offset 0, 3, 6, 9. And then, yeah, so we have the top left, we have the top right, we have the bottom left, and we have the bottom right. Just set the colors here. We'll create a function here in a second, which does this. But yeah, same thing, 3, 6, 9 for the first RGB, second RGB, third RGB, and fourth RGB. That's actually all the vertex data that is set. Finally, what we want to do is we want to set the indices. The indices, again, define where the triangles are. So we basically want to say that we have one triangle here, which is the first 3 here. And then we have a second triangle here, which is the second 3 here. So yeah, we build from the top left, top right, and bottom left. And then we build from the top right, bottom left, and bottom right. There we go. Second to last thing, we're going to add by 12 because we have XYZ, 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 and XYZ, for the positions, for example. And they're all the same. And then index, we have 6 as well. Finally, squeeze in, right? So 2 curly brackets there. And what we're going to do is we're going to actually buffer the mesh. And there we go. That is the last thing that we're going to do for this terrain. let's now do the cut. Let's do a really quick color convenience function. I forgot to do that. Come over here and let's go to util, and then we're going to go to, not util, sorry. We're going to go to visual and we're going to go to color.ts. Okay, and then add the following code here. This is just going to get a vector3 version of this color. I can type it out, and then yeah, it just appeared as a type up here. Cool. All right. Yeah, let's actually use this. So go into game and then main.ts. Now that we've done this, let's come over here and let's create a terrain. And let's see if we can type in terrain. We cannot. So let's come in here, import terrain from engine components terrain, and then it'll know. And then, yeah, so we created a terrain. And moment of truth, we have nothing. We broke everything. Come in here, let's actually get the terrain, and then let's say terrain dot update mesh. And we know that we have it. And there we go. We've got a terrain. The terrain, so you can do G, and yeah, terrain's very flat, but kind of boring. But we can change that. Come over here and let's add a function for that. To be honest, this is really annoying. Let's do an exclamation mark here. So we're doing an exclamation mark right here, and then we're going to loop through the terrain. And then let's come in here and let's actually set the terrain to a random between 0 and I think this. Come over here and let's see what happens. And yeah, now we have a final terrain going on here. So the terrain is kind of interesting because you can see, so there's each one of the cells and there's 2 triangles for each one. Oh, sorry, let me move my head. So yeah, there's the terrain here, and we have finally a terrain, and we have a bunch of floating watermelon all over the place. The terrain, you can see the lighting. I guess the light source is probably coming from over here and hitting it. So anything that is not, you know, that's kind of shaded, right? It's doesn't get as much light. Let's come in and we'll play around with this terrain a little bit now that we've done this, and you know, really good job for all your hard work in doing this. Let's come over here and let's set the terrain.cell size to 4, and we'll see what happens. And then yeah, so it stretches out that terrain significantly more as it generates it. You can even set the size of it. I'd be careful, but you can set the size of this. Let's come in here and we'll do 64, and we'll do 64. And yeah, on my, I mean, it's actually quite impressive. Like on my machine, it's not slow or anything. It's pretty fast. Yeah, let's go extreme. Let's go 256 and let's go 256. Oh, okay. Did it crash? Okay. Why, what happened here? Too many constructor arguments. All right, we'll have to figure that one out. But let's come in here and we'll do 64 and 664. Okay. And yeah, there we go. Okay, we have a large terrain. Now let's put a bunch of trees on this terrain. So again, in the description below, I have a tree texture as well. I'm just going to go ahead and bring this tree texture over to my assets, and I'm going to add it. I'm going to come over here. I'm going to import, just like we did the melon, I'm going to import the same thing. So let's come over here. We'll do, excuse me, we'll do that. We'll do tree. If I can type tree. Okay, so next let's create a tree texture. Similar to the watermelons, let's make a for loop. We'll maybe make 40 trees all over the place. Find a spot for each tree. So we're going to randomize it with a position and the scale. Now I set it to 64. Let's look at this. So the cell size is 4 and the terrain is 64. Let's set this back to 16 and 16. And then inside of here, let's come over. And then inside of here, let's go ahead and create each tree. Again, it's just a billboard. Instead of texture, we're going to use tree texture. Otherwise, it's going to be a bunch of watermelon. Let's come over here and see what happened. Now we've got, oh, let me make this bigger. And yeah, now we have tons of trees all over the place. And the trees are facing the player. And then over here in the corner, we have a bunch of watermelon doing that. Let's fix these watermelons real quick and then we'll close this video. So inside of here, the watermelons, the random is over here. We're randomizing the Y. Let's not do that. Let's randomize the Z coordinate. And let's come in here and we'll put each one of the watermelons at maybe like 0.5, just kind of elevate them a little bit. Later, we can make a function that does that. That figures out what spot it is in the terrain and does that. So yeah, we'll do that. And then let's come in here and let's see what's going on. So yeah, our watermelons are all over the place. Now you might notice every single time I refresh the page, I'm in this like really weird spot. Let's move the camera. So let's come over here, go ahead and place the camera in a nice position. And now every single time that you refresh the page, you're going to end up in a relatively nice position with the camera. And there we go. G moves up, H moves down, and look at that. We have a terrain, and then we've got trees, and we've got watermelons all over the place. Okay, we have done the basic starting code for our 3D RPG, and now we can just do really fun things from here. So if you've made it this far, I really want to thank you for, and just tell you, really good job with all of this. If you've gotten stuck on anything, again, the source code is all in the description below. And we'll keep doing videos like this to add to it. If you have suggestions for things that you'd like to cover or add, if you want to do quests, if you want to do NPCs, we can totally do that. I have another series where we did Pygame, and it was 2-dimensional, and it was, I had a lot of fun doing that. I'm really, really looking forward to doing 3D and going into that. Either which way, again, all the source code's in the description below. Thank you so much for watching, and I hope you have a good rest of your day.